Hi, my name is Xiangyue, and my student ID is DIC2509021. And I'm the first speaker of our group. Let me introduce my teammates first. Our group has Huang Yanxi, Qi Jianwen, Li Xiao, and me. You can see all our student IDs on this slide. Each of us will explain different parts of our project later. Our Calculus 2 project is called Designing the Most Cost-Efficient Beverage Can. We will use particle derivatives and language multipliers to find the cheapest size of drink cans. Today I will cover the title page, introduction and problem statement. Let's move to the next slide. Let's start with our project background. Almost everyone drinks candy drinks like cola, juice, or sparkling water every day. Factories make millions of aluminum cans all over the world every single day. The biggest cost for making cans is aluminum material. If we use less aluminum on each can, factories can save a lot of money. Besides cutting costs, less metal also helps protect our environment. We use fewer natural resources and create less waste. I will quickly talk about can recycling. After we finish drinks, empty cans are collected, crushed, melted, and made into new metal sheets. It only takes around 60 days to turn old cans into new ones, but recycling still uses a lot of energy. So the better choice is to reduce metal use when making cans, instead of only recycling waste later. One key point, tiny changes to a can's shape can bring huge savings for the whole drink industry. This makes us raise our research question. How can what we learned in calculus to help us find the most material saving and low cost size for beverage cans? We will answer this question in the following parts of our presentations. Now let's look at our problem statement and main goals. There is a cylinder on the slide, which stands for a drink can. It has R and H. We have three clear targets. First, we want to make the can's total surface area as small as possible. Surface area decides how much aluminum we need. Smaller surface area means less material and later production cost. Second, we have an unchangeable rule. The can's volume must stay fixed. A standard can holds 330 ml of liquid. We cannot make it smaller inside just to save metal. Third, less aluminum means lower factory costs and less harm to the environment. To make our math calculation simple, we set several basic assumptions. We treat the can as a perfect cylinder. We assume the aluminum sheet has the same thickness everywhere. We ignore small parts like the pull tab and lid edges. We also lay out small mistakes in real factory production. All these tiny details will make our equations too hard to solve. This is our full research process. Start with a real factory problem, turn it into a math model, use calculus to calculate the best size, and finally get the most cost-efficient can design. That's all for my sharing.
Hello everyone. Let's move on to developing the mathematical model to accurately describe our problem. We first define our variable definitions. R is the radius of cylinder, H is the height of the cylinder, V is the constant volume, and S is the total surface area. Our goal is clear. Find the values of the R and H that minimize the objective function S while keeping the volume constant. Please look at the cylinder diagram. The cylinder surface consists of two circular ends for the top and bottom, and one rectangular lateral surface. The top and bottom surface are each pi r square. When unfolded, the lateral rectangle has a width of 2 pi r and a height of h, giving an area of 2 pi r h. Adding this together gives our objective function, this one. And next page. Now let's look at applying the constraint. In manufacturing, the beverage volume must remain constant. The standard volume formula is pi r square h equal to v. To prepare for our calculus optimization, we rewrite this as a constraint function set to 0, as this one. And this constraint ensures every design stores the same amount of beverage. This constraint flow at the bottom summarizes our logic. A fixed volume leads to our constraint equation. From there, we can perform optimization to finally achieve the minimum surface area. This constraint is critical bridge between practical requirements and our mathematical calculations. And to solve this constraint problem, we use optimization using Lagrange multiplier. We introduce lambda, the Lagrange multiplier, to combine the objective function with the constraint into a single Lagrangian function. As shown in the formula, its components include the objective function 2 pi r squared plus 2 pi r h, which is the surface area to minimize the constraint pi r squared h minus v equal to 0, and Lagrange multiplier lambda, which adjusts the constraint weight. The key idea of the Lagrange multiplier concept is the geometric. At the optimal point, the gradient of the objective function is parallel to the gradient of the constraint. As the graph illustrates, this means the level curves of S are tangent to constraint curve. The point of the tangency gives the optimal solution. Mathematically, this is expressed as this one. Okay, thank you for listening. Let's welcome the next reporter. Thank you.
Hello, my name is Huang Yanxi and my student ID is 2509019. Now I will explain how we determine the optimal dimensions of the beverage can. After constructing the Lagrangian function, we take the partial derivative with respect to r, h, and lambda. Then we set all three partial derivatives equal to 0. This gives us three simultaneous equations, which will be solved in the next step to find the optimal radius and height. Okay, now let's solve this equation step by step. From the equation obtained by taking the partial derivative with respect to h, we have 2 pi r plus lambda pi r squared equal to 0. We rearrange the equation to express lambda in terms of r. This gives lambda equal to minus 2 over r. Next, we substitute this expression for lambda into the equation obtained from the partial derivative with respect to r. By replacing lambda, the equation now contains only the two variables, r and h. We simplify the equation by expanding and combining like terms. After simplification, we obtain the r equals to 2r. This is the most important result of our optimization. It tells us that the optimal can should have a height equal to its diameter. Finally, we substitute this relationship into the volume constant, pi r squared h equal to v. Okay, now the equation contains only one unknown variable, so we can calculate the optimal values of both r and h. Therefore, we have successfully determined the dimensions that minimize the surface area while keeping the volume constant. Okay, to verify our model, we use a beverage can with a volume of 330 cubic centimeters. Substituting this volume into our equations, we obtained an optimal radius of 3.74 centimeters, an optimal height of 7.49 centimeters. The minimum surface area is 263.93 square centimeters. This example shows that our mathematical model can be applied to real engineering problem. Now we'll hand over to my teammate for the result analysis.
My name is Qi Jingwen. My student ID is DSC2509035. I will talk about our project results, real-life uses, weaknesses, improvements, and final conclusion for the drink can optimization project. Let's start with slide 10, result analysis. If the can volume is fixed at 330 cube centimeters, our best mathematical design has a radius of 3.74 centimeters and a height of 7.49 centimeters. The height is almost the same as the diameter. The design gives the smallest surface area, only 263.93 square centimeters, so it uses the least aluminum metal. However, real Coca-Cola cans are very different. A real can has a radius of 3.30 centimeters and a height of 12.20 centimeters. Its surface area is over 300 square centimeters. This design uses more metal and costs more money to make. You may ask, why do factories now use our better short and wider can design? There are four simple and important reasons. First, structure strength. Short and wide cans are easy to get pressed and broken during shipping. Tall and narrow cans are stronger. They can hold more weight without damage. Second, shipping and storage. Tall thin cans fit better into standard boxes and supermarket shelves. They share more transport cost. The saving is more important than saving metal. Third, hand feeling. Short wide cans are hard and comfortable to hold. Tall can fit our hands easily, so they can more user-friendly. Fourth, self and design. Tall can have more space for brand logos and product information. This helps brands sell more products. For these real-life reasons, factories do not fully follow the perfect man design. Now, slide 11, applications weakness and the future and changes. The mass optimization. Mass is very useful in industry. This helps drink companies save lots of aluminum every year. We can also use these methods for other cellular packages such as energy drink cans, food cans, and cosmetic tubes. Using less aluminum reduces waste and pollution, which helps green production. At the same time, our model has some small weaknesses. We assume that can metal has the same thickness everywhere. In real life, can top and bottom are thinner for safety. We also did not count the material for cans tips, cells edges, and thickness spaces. We ignored factory machine limits and safety rules. To make the metal better, we have three improvements. First, we can add different metal thickness to our calculations to match real factory production. Second, we can create a better system to balance the cost, can strengthen and head feel at the same time. Third, we can add the shipping and size limits into our mass reels, so the final design is more suitable for rail transport and shortage. Finally, Set 12, Conclusion. This project shows that college calculus knowledge works well for real-life problems. Practical derivatives and language multipliers helps us find the best shape with the least material and the fixed volume. This math method is simpler and more effective than basic substitution calculation. Our study brings two big benefits. Lower production costs, more environmentally friendly. Manufacturing real cans are not exactly the same as our ideal design, but our data gives factories a clear standard to calculate extra material cost. In short, the project connects subtract math knowledge with daily products. Mathematical modeling helps companies balance cost, material use, sustainability, and users' experience. Thank you for listening.